LeetCode Problem 42, Trapping Rainwater, isn't just a quirky challenge. It models real systems, terrain modeling, civil engineering, even compiler memory profiling. Each bar is terrain height, and trapped water is wasted space. But here's the twist. Inefficiency stacks up fast. So how do we avoid recalculating boundaries and start coding smarter? All right, ducklings, let's splash into the brute force approach. It's not fast, but it checks all possibilities. Time to see what that looks like in code. First, we grab the length of the elevation map and set up a variable to track how much water we've collected. We scan each bar starting from the second and stop before the last. Edges can't trap water since they don't have neighbours on both sides. At each step, we create two trackers, one for the tallest bar to the left and one for the tallest to the right. They'll help define the water level here. To find the left boundary, we scan backward from the current index to the start, updating the tallest seen so far. Then we do the same going forward, scanning from the current index to the end to find the tallest bar on the right. With both sides known, we compute water at this bar by subtracting the bar's height from the smaller of the two boundaries, only if the result's positive. Add that to our total. After checking all bars with neighbours, we return the total water trapped. This brute force version runs in big O of n squared time, which means 100,000 bars could mean 10 billion operations. Not ideal. Space is big O of 1, but performance takes a dive at scale. So how can we cut out the waste? Let's stop repeating work and use some extra space to track boundaries efficiently. We start by getting the size of the height array and handling the edge case. If it's empty, there's no terrain, no water. Now we set up two arrays to store the tallest bar to the left and right of each index. These will make future calculations quick. For the left max array, the first element just copies the first height. There's nothing to the left of it. We fill the left max array by moving left to right, updating with the tallest bar we've seen so far. Next, we set the last value in the right max array to the last height, since there's nothing beyond it. Then we build the right max array in reverse, tracking the tallest bar seen from the right at each step. With both arrays ready, we loop through the elevation map and calculate trapped water at each index using the minimum of the two max heights minus the current bar's height. Add up the trapped water at every index, and that gives us our final total. This version runs in big O of n time, around 200,000 operations for 100,000 bars. Way faster. The trade-off is big O of n space for those two arrays. Usually fine, but something to watch in low memory environments. So how do we keep that speed but ditch the extra space? Let's shift to a more space-efficient approach. We kick things off with two pointers, one at each end, and two variables to track the tallest walls seen so far on each side. We'll also set up a counter to collect trapped water as the pointers move inward. This loop runs while the pointers haven't crossed. At each step, we compare wall heights and process the side with the shorter wall. If the left wall is shorter, that side controls the limit, so we process the left pointer first. If the current left height is the tallest we've seen on the left, we update the max. Otherwise, we calculate trapped water based on the left max. Then we nudge the left pointer one step to the right. But if the right wall is shorter or equal, the right side limits the water, so we process the right pointer instead. Again, we either update the right max or calculate trapped water based on it. After handling the right, we move that pointer one step to the left. When the pointers meet, the loop ends. We've tallied all the water and we're ready to output the result. This is the optimal method, still big O of n time, but with big O of 1 space. It's lean, fast, and fits real-world constraints, exactly what top-tier interviews look for. So we waddled through brute force, slow, but it works. Then we upgraded with pre-computed boundaries, fast but memory hungry. Finally, we glided into the two-pointer method, same speed, zero extra space. That's not just clever, it's the kind of balance real systems thrive on. In interviews, this trick shows you know how to think in trade-offs. Want to master it? Watch for two-pointer patterns in streaming data, sliding windows, or in-place algorithms. Keep sharpening your instincts and keep solving smart.